Equilibrium. It's pretty much what it says it is. It's a state of balance. Essentially, no acceleration. An object either at rest or with constant velocity. We will focus on objects that are at rest. There will be no linear acceleration. Sometimes that will be phrased as no translational acceleration. F net is 0 according to Newton's second law. But the new thing is we will also have no rotational acceleration. The net torque will be 0. The torques will be balanced. The clockwise torque will equal the counterclockwise torque. Now we'll need to give you several examples here. Let me draw this one out here. We have a trapeze bar. And this trapeze bar is like, it's one of these like bars that an acrobat, like at a circus, would be swinging from. It has two ropes on either end, represented by the red arrows pointing up, holding up the trapeze bar. But here I have not a person hanging from the trapeze bar, but two masses, 8 kilograms and 13 kilograms. Now what we want to find is the tension in each of these two ropes. Looking at the left-hand side, I want to call that one T1, the tension in rope number 1, and on the right-hand side, T2, the tension in rope number 2. The dimensions given here are that from the left end, T1, to the 8 kilogram mass is 30 centimeters. From one weight to the other in the middle there, it's 40 centimeters, and from the 13 kilogram weight or mass to the right-hand side is 25 centimeters. All right, now here is the technique that I like to use. What I will be doing with all these torque problems where we have equilibrium is I will draw the new simplified free body force diagram. This line right here that I just drew represents that trapeze bar in more simple form. Now there are four forces acting on this trapeze bar. In this case, it does say in the material here that it's a massless horizontal bar. We'll step up our game a little bit in the next problem or two where we're going to have objects themselves that have mass that we have to add to the diagram. But the bar itself doesn't weigh anything. We have a rope on the left-hand side with a tension we don't know yet. We want to find that out. On the right-hand side, a rope with tension 2. Those are forces. Here we have an 80 Newton force. 8 kilograms times 10 meters per second squared gives you 80 newtons of force. That's the weight. And 130 newtons of force. There's our free body force diagram. These all need to be balanced. So as we look forward here, T1 plus T2 must equal 210 newtons because we have 210 newtons of force down. We will need 210 newtons of force straight up. The other thing that's implied that you will assume, unless you're told otherwise, all the angles are at right angles. You'll see me calculate that in a few minutes, but because they're right angles, the sine of 90 will be 1, and it will be a non-factor in the problems. So the distances are still, and I'm going to simplify this. This distance is 30. This distance here is 40. That's between the two masses. And then 25. Those are all centimeters. But the simplified diagram there. Now here's what I like to do, is I like to label where all these forces are applied. I'm going to highlight them with dots. I'm going to call that point A. I'm going to call this point B, point C, and point D for lack of creativity. A, B, C, and D. There's 4 forces applied at those 4 points. What you need to do now is pick one of those 4 points, and it doesn't matter. I'm going to do this problem twice just to show you. If I pick point A as my reference point, so I'll do the calculation over here. So point A is my reference point. And what I want to do is balance out the torques. I want my clockwise torque to equal my counterclockwise torque. Now, it seems very simple. Clockwise is the way that the hands on a clock travel. Counterclockwise is the other rotational direction. But it's easy to mess this up. For example here, if I take point A as my reference point, and one way to think of this is it's a point that's kind of like the middle of the clock, where you have the hands of the clock, and I like to think of the bar here, my horizontal bar, as like the second hand on the clock. Or another way to think of it is this. If I were to cut rope T2, what would happen if rope T1 is still intact? What would happen to this horizontal bar? Well, it would swing down because B and C, or the forces at B and C, are pulling down, trying to make the whole thing rotate clockwise. Whereas T2, that rope that I just cut, is pulling up, trying to, if it was stronger, or somebody grabbed onto it and pulled up, would make the whole system rotate counterclockwise if you held point A fixed. Anyways, the calculation will then look like this. The clockwise torque is the sum of two torques. The 80 Newton force is pulling down at point B. So once again, torque is force times distance. 80 newtons times the distance, it's 30 centimeters, and I will do this in centimeters. You can do this in Newton centimeters or Newton meters, times the sine of 90, because the 80 Newton force is at right angles with the beam, plus the 130 times its distance. Now, since we're using point A as our reference point, we have to measure everything from where our force is all the way back to point A. So the 130 Newton force is at point C, all the way back to point A is 70 centimeters times the sine of 90. And that's going to equal, a lot of space here, my counterclockwise torque. And there's only one force that's creating counterclockwise torque with reference to point A, and that's my T2, my rope T2. It's the force T2 times its distance all the way back to point A. That's 95 centimeters times the sine of 90. Now you might say, well, what happened to T1? Well, T1 generates no torque with respect to point A because its distance from point A is 0. So it would be a force of whatever, unknown, doesn't really matter, times a distance of 0 will give you 0 torque. That's the beauty of picking point A, is that it gets rid of T1. Now I need to solve this. I have 80 times 30, which is 2400, so I can put 2400 plus 130 times 70, that's 9100, equals the T2 times 95. And the sines of 90 all cancel out, well, because sine of 90 is 1. I really didn't even need to write them down. So I add the 2400 plus the 9100 and divide by 95, and then T2 comes out to be, in this case, 121 newtons. That's my answer for the tension in T2. All right, let me show you another technique. I could have, and this is now just bonus material, I could have calculated this another way. I could have taken point D as my reference. I just want to show you this because you could pick any one of the 4 points, but some points are easier to use than others as far as calculating the balanced torques. If I would have picked point D, and you could have picked points A, B, C, or D. B and C would have been bad for reasons you'll see later on. But point D, once again, to do my clockwise torque equal to my counterclockwise torque, so I'm going to apply the same principle down here. At point D now, things shift a little bit. If now, for example, if I'm holding point D steady and I cut the rope, T1, if I cut T1, the 80 Newton force and the oar, both, 80 and the 130, both are pulling down, they would make the whole thing swing counterclockwise now with respect to point D, because point A would fall if you cut rope T1. Or, once again, with respect to point D, T1 is pulling up, trying to make the whole system go clockwise. So now the only clockwise torque will be generated by T1. You would have clockwise torque T1 times the whole distance from point A to point D, which is the 95, equals the counterclockwise torque now, which would be the sum of the two forces that are, or torques that are generated by the 80 and the 130. So it's going to be equal to the 80 times its distance, which is 65 centimeters, plus the 130, once again measuring everything from point D, times 25. And noticing I'm leaving off the sine of 90 now. If it's sine of 90, you do not need to write it. Anyway, now, if you solve this, you end up with T1 equal to 89 newtons. You can check that yourself. to see if the math works out there. But what's good about that is if you look at your T1 and T2, if you add them up right now, T1 plus T2, what you'll notice is that T1 plus T2, 121 plus 89 equals, I believe, 210 newtons, which it needs to do because the upward T1 plus T2 have to equal the downward 80 plus the 130. So we have 210 newtons up, 210 newtons down. So that's just a check there. That 210 newtons is a check. But a really observant person now could figure this out. For example, once we did the first calculation for T2, we got to 121 newtons for T2. We didn't need to go through the blue calculation here for T1. We did not need to do the torque with respect to point D. That was good practice, but the shortcut would have been, well, once we have T2, all you needed to do is take the 80 plus the 130, which is 210 newtons down, and subtract the 1 up, the 121 up, would have given you the 89 newtons up for T1. So there are some options here in these problems.